Algebraic Structures, Lecture 16, Separable and Normal Extensions. Let us first discuss the notion of derivative for polynomials. Let K be a field, and K of x the polynomial algebra over K in one variable x. Recall that the derivative map, which is usually denoted by primed, that's a map from the polynomial algebra to itself, which is defined by the following formula. If we take the derivative of the polynomial a0 plus a1x plus a2x and so on, the outcome is the polynomial a1 plus a2x plus a3x squared and so on. This map has the following properties. First of all, that's a linear map. So if we take the derivative of a constant times a polynomial, we can take the constant out of the derivative. Then the derivative of the sum of two polynomials is equal to the sum of the derivatives. Next, it obeys the Leibniz rule. If we take the derivative of the product of two polynomials, the outcome is equal to the sum of the following two summands. The first summand is the derivative of the first polynomial times the second one, and the second summand is the first polynomial times the derivative of the second polynomial. Moreover, if the characteristic of the field is 0, then the derivative of a polynomial is equal to 0 if and only if this polynomial is a constant. So it has degree 0 or is 0 polynomial. Furthermore, if we have a polynomial which has degree strictly greater than 0, then the degree of the derivative of this polynomial is equal to the degree of the original polynomial minus 1. It is important to note that if the characteristic of our field is a prime p greater than 0, then there exist non-scalar polynomials with 0 derivative. For example, x to the power p is such a polynomial, because when we derive this, we will get p times x to the power p minus 1, and p is equal to 0 if the characteristic is p. Now we can define the notion of a separable polynomial. Let K be a field, and K of x the polynomial algebra over K in one variable x. Definition: an irreducible polynomial f of x over K is called separable, provided that its derivative is non-zero. For example, if the characteristic of the field K is 0, then every irreducible polynomial is separable. Example 2. Here's an example of a non-separable polynomial. Consider the field f2, which is z2, the field with two elements. So we are in characteristic 2. Next, consider the field of rational functions in the variable t over our field f2. Then we have the field extension. We can look at f2 of t, and inside we have the field of rational functions in t squared. And then the polynomial x squared plus t squared is the minimal polynomial of the element t over f2t squared. So in particular, this polynomial is irreducible because it's a minimal polynomial, and its derivative is clearly equal to 0. So this polynomial is not separable. Separable polynomials are important because they control the multiplicity of roots for irreducible polynomials. Proposition: let f of x be an irreducible polynomial over the field K, and let f be the splitting field of this polynomial. Then the polynomial f of x is separable if and only if it doesn't have multiple roots in the splitting field f. Proof: first we assume that f prime is different from 0. Then, of course, from the definition, the degree of f prime is strictly smaller than the degree of f, and since f of x is irreducible, it follows that f of x and its derivative are relatively prime. So the greatest common divisor of them is equal to 1. If a is a root of f of x, of course in f, we don't assume that those roots exist in the field K, then we can write f of x over the field f as x minus a to some power m times g of x, where m is a multiplicity of this root. And then the derivative of x is equal to m times x minus a to the power m minus 1 times g of x plus x minus a to the power m times g prime of x. In particular, if our multiplicity is greater than 1, it follows that x minus a is a common factor for both f and f prime. And this contradicts our assumption that f and f prime are coprime. Conversely, if we assume that f of x is equal to x minus a times g of x, with g of a non-zero, so if the root a is simple over f, then f prime of x is equal to, so we use the Leibniz rule, g of x plus x minus a times g prime of x. If we now insert x to be equal to a, we get that f prime of a is equal to g of a, and this is non-zero. And this of course means that f prime is a non-zero polynomial, because it has a non-zero value at some point. And this completes the proof of our proposition. Now we can talk about separable extensions. Let K inside F be a field extension. Definition: an algebraic element A in F is called separable over K, provided that its minimal polynomial is separable. Another definition: an algebraic extension K inside F is called separable, provided that every element of F is separable over K. For example, an algebraic extension in characteristic 0 is always separable, because in characteristic 0, all irreducible polynomials are separable. And one more definition: a field K is called perfect, provided that all irreducible elements in K of x are separable. So for example, any field of characteristic 0 is perfect. So this separability thing is only an issue if the characteristic is non-zero. Now we formulate our first main result for today's lecture, and this is the theorem about separable extensions. Theorem: let K inside F be a finite extension of degree n, so the dimension of F over K is n. Then the following conditions are equivalent. Condition 1: this extension is separable. Condition 2: F is obtained from K by adjoining a finite number of separable elements over K. Condition 3: for any field homomorphism phi from little k to capital K, there is a field extension, the capital K inside the capital field L, such that phi has n different extensions to homomorphisms from F to L. And condition 4: there is a field extension of little k inside capital M and n different homomorphisms from F to M, such that they are equal to the identity when restricted to K. Let us prove this theorem. Clearly, the first condition implies condition 2. So indeed, if the extension is separable, then the bigger field is obtained from the smaller field by adjoining a finite number of separable elements. Also, condition 3 implies condition 4 if we take as phi the natural inclusion of K to F. So if you look at conditions 3 and 4, and instead of this capital K take the field F and the natural extension of K to F, then condition 3 implies condition 4. So let us prove that condition 4 implies condition 1. Assume that A is a non-separable element in F. Consider the minimal polynomial of A, ma of x, and assume that it has degree d. And let capital P be the field which is obtained by adjoining to K our element A. If psi is a homomorphism from P to any field M, then if we assume that psi is the identity on little k, the element psi of A will be a root of our minimal polynomial, and since P is obtained from K by adjoining A, this uniquely determines the homomorphism psi. Since our minimal polynomial has multiple roots, the total number of different roots and thus different homomorphisms from P to M, is strictly smaller than the degree d of the minimal polynomial. Next, we observe that the dimension of f over p is equal to the ratio of the dimension of f over k divided by the dimension of p over k. This is equal to n divided by d. And by a corollary from the previous lecture, each homomorphism from P to M has at most degree of f over p, that is n divided by d extensions, to a homomorphism from f to m. So we have n divided by d times something which is strictly smaller than d, that together gives us something which is strictly less than n, homomorphisms from f to m, which are identity on k. And that contradicts condition 4. So this proves that condition 4 implies condition 1. It remains to prove that condition 2 implies condition 3. And in order to prove this, we proceed by induction on k. So we assume that f is obtained from little k by adjoining one separable element a. Then the degree of the minimal polynomial of this element a is equal to n. That's exactly the dimension of f over k. Consider the image of this minimal polynomial under our homomorphism phi. Let's call this image f of x. And let capital L be the splitting field of the polynomial f of x over k. Since we assume that ma of x is a separable polynomial, the greatest common divisor between this polynomial and its derivative is 1. And so if we apply phi, we get that the greatest common divisor between f of x and f prime of x is 1. And this implies that f has n different roots in our field L. We can send x to each of these n different roots, and this will give us n different homomorphisms from the polynomial algebra in the variable x over k to L. And these induce n different morphisms from f to L, because f is a quotient of k of x modulo the ideal generated by the minimal polynomial. And this proves the induction basis. And the induction step is similar when we do the same thing as in the basis by adjoining one element at a time, and using that when we have a flag of field extensions, the degree of the biggest one over the smallest one is just the product of the degrees of the extensions with the intermediate field. Okay, so this completes the proof of our theorem for separable extensions. And now we can characterize the perfect fields. Perfect fields, these are fields over which all irreducible elements are separable. So theorem, any field of characteristic 0 is perfect. A field k of characteristic p greater than 0 is perfect if and only if, for any a in k, there is b in k such that b to the power p is equal to a. In other words, we can take the p's root out of any element in our field. Proof. In characteristic 0, all irreducible polynomials are separable, we know this, so the claim is clear. So let the characteristic of our field k to be equal to p, which is greater than 0. Then, if we have a polynomial in a variable x over k, the derivative of this polynomial is 0 if and only if this polynomial is in fact a polynomial in x to the power p. The only powers of x which appear should be the powers of p, because then if we derive, we will have a multiple of p times something, and the multiple of p is 0 in characteristic p. Also note that in characteristic p, sending an element to its p's power is a field homomorphism. So namely, that's because the p's power is an additive function in characteristic p. U plus v to the power p is equal to u to the power p plus v to the power p, and that's because p divides all non-trivial binomial coefficients p choose I, so where I is different from 0 or p. Therefore, if we know that each element in our field has a pth root, then if we have a polynomial in x to the power p, we can use that taking the power p as a field homomorphism and each coefficient has a piece root, we can write it as piece power, we will get that this polynomial is in fact a piece power of a polynomial in the variable x. In other words, this means that any polynomial in x to the power p is reducible. And so for an irreducible polynomial, the derivative will not be zero. This proves one part of our theorem. So this shows that under this condition k is perfect. And the second part, let us assume that k has an element a, which does not have any piece root in k. And then we claim that the polynomial x to the power p minus a is irreducible. And of course its derivative is zero. Indeed, let b be a root of this polynomial in some field extension f of k. Then x to the power p minus a is equal to x minus b to the power p over f. That's because taking the power p is an automorphism, so x minus b to the power p is equal to x to the power p minus b to the power p, and b to the power p is a. Now, if some f of x divides x to the power p minus a, then, from the previous formula, we know that f of x should be x minus b to some power I, where I is between 0 and p. So assume that I is strictly greater than 0 and strictly less than p. Then x minus b to the power I, when we write it over f, it will be x to the power I plus I times b times x to the power I minus 1 plus and so on. But I is an integer, and b is an element of f which doesn't belong to k. And so ib doesn't belong to k. So this polynomial cannot be a polynomial over k of x, and this means indeed that x to the power p minus a is irreducible. And as we already mentioned, its derivative is obviously zero, so this gives us that our field k is not perfect. Finally, let us talk about normal extensions. Let k inside f be a field extension. Definition: this extension is called normal, provided that any irreducible polynomial f of x over k that has a root in a field f splits over the letter field into linear factors. So if it has one root in f, all roots of this polynomial should belong to f. For example, if f is algebraically closed, then any extension of k inside f is normal. Example 2. The extension of rational numbers inside rational numbers with minus cubic root of 2 adjoint, this is not normal. Indeed, we looked at this example during the last lecture, where we saw that the polynomial x cubed plus 2 is irreducible over q. So that's the minimal polynomial of the element minus cubic root of 2. Moreover, the splitting field of this polynomial, we computed it during the last lecture, and it was strictly larger than q with the cubic root of 2 adjoint. In fact, in order to get the splitting field, we need to adjoin both the cubic root of 2 and also the element 1 plus the square root of 3i divided by 2. This tells us that the extension of q inside q with the cubic root of 2 adjoint is not normal. Now let us prove the following theorem about normal extensions. Let k inside f be a finite extension. Then the following conditions are equivalent. Condition 1, this extension is normal. Condition 2, f is the splitting field of some polynomial f of x over k. And condition 3, for any field extension of f inside k, and any field homomorphism phi from f to k, which is the identity on k, phi sends f to f. Proof. Let us start with proving that condition 2 implies condition 3. So we assume that our field f is a splitting field of some polynomial f of x. Let a1 and so on ak be all roots of f of x. Then, of course, f is obtained from little k by adjoining all these roots a1 and so on ak. The homomorphism phi sends each ai to some aj, and that element is in F. Therefore, since phi is fully determined by its values on k, which is the identity, and on all the roots, and the image of every root is inside F, it means that phi sends F to F. And this establishes condition 3. Next, let us prove that condition 3 implies condition 1. Let g of x be an irreducible polynomial over k, and a an element in F such that g of a is equal to 0. Let capital K be the splitting field of g of x over F. And let b in this capital K be some root of g of x. Then there is a homomorphism psi from little k with an element a adjoint to F with b adjoint, which sends a to b, such that this homomorphism psi is the identity on k. So using the theorem about extension of homomorphisms from the previous lecture, we can extend psi to a homomorphism from F to some extension capital L of F with b adjoint. And by condition 3, this extension must map F to F, but it maps A to B, which implies that B is in F. And this implies condition 1. So all roots of our g of x are already in F. Finally, let us prove that 1 implies 2. Assume that our field F is obtained from K by adjoining the roots a1, a2, and so on ak of our polynomial f of x. Then the minimal polynomial for each of these ai's splits over our field F into linear factors. And this means that our F is a splitting field of the product of all these minimal polynomials. And this completes the proof. Now let us look at one example. Example: for n greater than 1, consider the field extension of rational numbers into the field F, it will depend on n, which is obtained from rational numbers by adjoining the element psi n, which is the complex root of unity of degree n. So that's a primitive complex root of unity of degree n, which is given by the formula cos of 2 pi divided by n plus sine of 2 pi divided by n times I. Note that we are in characteristic 0, so this extension is automatically separable. Also, the field F, by definition, contains all powers of psi n. So if it contains psi n, it of course contains all powers. Psi n is a primitive nth root of unity, and so it follows that F contains all nth roots of unity. In other words, F is the splitting field over Q of the polynomial x to the power n minus 1. Therefore, this extension is also normal. So this is a typical extension which is both separable and normal. Note that the polynomial x to the power n minus 1 is not irreducible over Q. So for example, we can write x to the power n minus 1 as x minus 1 times x to the power n minus 1 plus x to the power n minus 2 plus and so on plus 1. So if n is greater than 1, this is not an irreducible polynomial. More generally, similarly, we see that if k divides n, then x to the power k minus 1 divides x to the power n minus 1. So let us define the polynomial phi n of x at the minimal polynomial of psi n of x. Then we can write phi n of x as a product over all k which are coprime to n, so such that n and k have greatest common divisor 1, of the linear factor x minus psi n to the power k. Consequently, the polynomial x to the power n minus 1 splits into the product of phi k of x over all divisors k of n. So for example, if n is prime, then phi n of x is just x to the power n minus 1 plus x to the power n minus 2 plus and so on plus 1. So these polynomials phi n of x are usually called the cyclotomic polynomials, and here are the examples for small values of n. So if n is equal to 1, then phi 1 of x is x minus 1. So phi 2 of x is x plus 1, because 2 is a prime number. Phi 3 of x is x squared plus x plus 1. Phi 4 of x is x squared plus 1. Phi 5 of x is x cubed plus x squared plus x plus 1. That's because 5 is a prime number. Phi 6 of x is x squared minus x plus 1. Phi 7 of x, 7 is a prime number, it's x to the power 6 plus and so on plus 1. Phi 8 of x is x to the power 4 plus 1. Phi 9 of x is x to the power 6 plus x to the power 3 plus 1. And phi 10 of x is x to the power 4 minus x to the power 3 plus x to the power 2 minus x plus 1. Here are some additional problems and questions at the end. Problem question 1. Prove with all details the induction step in the theorem on separable extensions. Problem question 2. Prove that the derivative of f of g of x is equal to f prime of g of x times g prime of x. Problem question 3. Prove that any extension of degree 2 is normal. Problem question 4. Prove with all details that the map which sends a to the power p is a field homomorphism, it should be homomorphism, is a field homomorphism over a field of characteristic p. Not any element in our field is expected to have a piece root. And problem question 5. Prove with all details that phi n of x is equal to the product over all k such that the greatest common divisor between n and k is 1, and then we take x minus psi n to the power k. Thank you very much, and see you next time.